Stars die in explosions. We know that. A flash in the sky. A nebula left behind. But what we call a supernova is not one thing. The universe has invented 7 ways to blow up a star. 7 mechanisms so extreme they push physics to the limit. Some leave nothing, some forge gold. One tears through reality with jets moving at 99% the speed of light. Which one is the most powerful? Which leaves a black hole? And which type exploded before any human existed to record it? Every category tells a different story. Not all stars die the same. Mass, spin, metallicity, binary partners, these variables change everything. A sun 40 times our mass dies differently than one 200 times larger. A star with a companion dies differently than one alone. Chemistry matters, speed matters, and when the conditions line up just right, the universe delivers something so bright it outshines 100 billion suns. If you value documented stellar physics and extreme astrophysics history like this, subscribe. It's the best way to support our work. Also, comment from which city you're hearing this from. This script is researched and factual, using sources from the monthly notices of the Royal Astronomical Society, published in November 2024, documenting superluminous supernovae catalogs with over 262 events. Nature Astronomy's June 2021 paper identifying the first confirmed electron capture supernova, and ArcSIF preprint server October 2024 showing fresh analysis of pair instability candidates, including SN 2018 IBB, which radiated over 3 times 10 to the 51st ergs. These are peer-reviewed sources with data validated across multiple telescopes and gravitational wave observatories. Now back to the information. Number 1, pair instability, supernova. Stars between 130 and 250 solar masses exist in a mass range so extreme they cannot leave a remnant. The core temperature climbs so high that gamma rays spontaneously split into electron-positron pairs. Every photon that converts loses its outward pressure. The radiation that held the star against gravity vanishes in microseconds. Pressure drops. The core collapses. But this collapse is different. Oxygen fusion ignites in a thermonuclear runaway. The entire star detonates. No neutron star. No black hole. Complete annihilation. The explosion ejects up to 57 solar masses of radioactive nickel-56. That decay powers a light curve lasting hundreds of days. Peak luminosity reaches 10 to the 44 ergs per second. That is 100 times brighter than a typical core collapse supernova. These events likely dominated the early universe when population 3 stars formed from pure hydrogen and helium. Zero metallicity, masses reaching 300 suns, short lifetimes, then pair production instability and obliteration. Theoretical predictions go back to 1967. Barkett, Riccavi, and Sack published calculations in physical review letters showing pair production could destabilize massive stellar cores. For decades, no confirmed detection existed. SN 2006, JAI in 2006 showed extreme luminosity, 2.4 times 10 to the 44 ergs per second at peak, distance 73 megaparsecs. Host galaxy NGC 1027. The progenitor mass estimates ranged from 100 to 240 solar masses, but contamination from circumstellar interaction complicated the analysis. The spectrum showed hydrogen. True pair instability. Supernovae should be hydrogen poor. The star's envelope would have been lost long before core collapse. So 2006 sky remains disputed. SN 2018 IBB provides stronger evidence. Discovered at redshift 0.166. Monitored from mid-2018 to early 2022. The bolometric light curve peaked above 2 times 10 to the 44 ergs per second. Rise time exceeded 93 rest frame days. That long diffusion time requires enormous ejected mass. Spectral modeling suggested minimal hydrogen. The light curve decay matched nickel-56 and cobalt-56 radioactive chains. Total radiated energy surpassed 3 times 10 to the 51 ergs. Monthly notices of the Royal Astronomical Society published detailed analysis in March 2024. Multiple research groups modeled the progenitor. Helium core mass estimates ranged from 65 to 130 solar masses. The explosion energy approached 10 to the 53 ergs. For comparison, a typical supernova releases 10 to the 51 ergs, 100 times less. The ejecta contained multiple solar masses of iron group elements scattered into the intergalactic medium. Those heavy elements seed future star formation. Future generations inherit the chemical signature. But pair instability events exist on a continuum. Stars between 100 and 130 solar masses undergo pulsational pair instability. The core produces pairs, pressure drops, partial collapse, oxygen ignites, but the ignition is not strong enough to destroy the star completely. The outer envelope ejects 10 to 25 solar masses blown off. The core survives, oscillates, settles, evolves again. Then, if the helium core still exceeds 100 solar masses, the cycle repeats. Pulsational events produce supernova imposters, bright outbursts, months-long plateaus, then fading. Observers see what looks like a supernova, but the star remains. Eta Carinae's 1843 eruption may fit this pattern. The Great Eruption. Luminosity spiked. Mass loss reached 10 solar masses. The star survived. Still shining today, still unstable. Still a candidate for full pair instability when the core finally reaches critical conditions. If Eta Carinae explodes as a true pair instability event, Earth sits 4,500 light-years away. The flash would be visible in daylight, brighter than the moon, lasting months. Number 2, superluminous supernova. These are the showstoppers. Peak magnitudes reaching minus 22.5 or brighter. Luminosity 10 to 100 times normal supernovae. Duration, hundreds of days. First discoveries came from Palomar Transient Factory and Pan-STARRS around 2010. By December 2022, astronomers had cataloged 262 Type 1 superluminous events. Type Y means hydrogen-poor spectra, stripped envelope. The core collapses, but the energy source for the light curve is debated. 3 mechanisms compete. Magnetar spin-down, circumstellar interaction, radioactive decay. Monthly Notices published the comprehensive catalog in November 2024, compiling 30,000 photometric detections across ultraviolet, optical, and infrared bands. The Magnetar model proposes a rapidly spinning neutron star forms during core collapse. Rotation periods under 10 milliseconds, magnetic field strength 10 to the 14th Gauss, or higher. The spin-down timescale is days to weeks. Rotational energy transfers to the expanding ejecta. The ejecta reprocesses that energy as optical light. Observed light curves match Magnetar spin-down predictions for many events, but some show periodic modulations, bumps in the light curve. SN 2024, AFAV displayed a chirp signal. The period decreased from roughly 20 days post-peak to shorter intervals over 125 days. Standard Magnetar models predict smooth, monotonic decline. The chirp requires additional physics, lens-Thirring precession. Frame dragging by the spinning Magnetar tilts an accretion disk. The disk's inclination wobbles. The wobble modulates the energy output. The precession period shortens as the disk accretes and spirals inward. ARXIV published the analysis in September 2025. The model fits SN 2024 AFAV and retroactively explains earlier events like SN 2018 KIT and SN 2021 MKR. Those were attributed to circumstellar interaction or magnetic inclination changes. Lenzy-Thirring offers a unified explanation. General relativity imprints its signature on a supernova light curve. Circumstellar interaction models attribute the brightness to shock heating. The supernova ejecta slams into dense material previously ejected by the progenitor. The collision converts kinetic energy to thermal radiation efficiently. Shock temperatures exceed 10,000 Kelvin. The ejecta decelerates. The shock compresses and heats the circumstellar shell. Hydrogen emission lines appear narrow. That narrow line width tags the stationary pre-ejected material. Type 2 superluminous events show hydrogen. Type I events show circumstellar interaction, but from helium or carbon-oxygen shells. The progenitor lost its hydrogen envelope earlier. Binary mass transfer, Wolf-Rayet winds, luminous blue variable eruptions. The star shed layers before the final explosion. Superluminous supernovae prefer low metallicity environments. Host galaxies typically have stellar masses under 10 to the 8th solar masses. Specific star formation rates around 10 to the minus 9 per year. High star formation, low metal content, extreme emission line galaxies. Monthly Notices published environmental studies in July 2023 showing only 3% of superluminous hosts occur in high-density galaxy clusters. The galaxies favor isolated regions. Low metallicity allows massive stars to retain more mass. Higher metallicity drives stronger stellar winds. Winds strip the envelope. The star loses mass. Final core mass determines explosion mechanism. Low metallicity equals higher core mass equals more extreme death. The most distant spectroscopically confirmed superluminous event sits at redshift 2.011, SN 2025 WMNI, discovered by Zwicky Transient Facility on September 1, 2025, gravitationally lensed by a foreground galaxy cluster, magnification factor 20 to 50. The lensing amplified the brightness. Multiple images resolved with 1.7 arc-second separation. LRIS spectroscopy at Keck Observatory confirmed the redshift and classification. The spectrum showed broad absorption features from carbon magnesium, silicon titanium iron. Blue colors, rapid evolution. UV luminosity unusually high, either intrinsically overluminous or observed at an earlier phase than typically possible, or the lensing magnification exceeds 50. ArcSIF posted the discovery in October 2024. Strong gravitational lensing opens a window to study superluminous events at cosmic distances where they would otherwise be too faint. Number 3, hypernova/collapsar. Core collapse on steroids. Kinetic energy exceeding 10 to the 45 joules, an order of magnitude above standard supernovae. Ejecta velocities reaching 30,000 kilometers per second, 10% light speed. Expansion so fast, the spectral lines broaden into unrecognizable blurs. These come from stars above 30 solar masses. Stripped of hydrogen and helium, bare carbon-oxygen cores, the core collapses, forms a black hole. But the collapse happens so fast the outer layers do not know. An accretion disk forms around the newborn black hole. The disk launches relativistic jets. Twin beams of plasma accelerate to 99% light speed. The jets drill through the stellar envelope, emerge from the poles, plow into surrounding material. The jet interaction creates a gamma ray burst, GRB, duration 2 seconds to minutes. The longest bursts correlate with hypernovae. GRB 030329 on March 29, 2003. Detected by NASA's High Energy Transient Explorer, duration over 30 seconds. Localized to constellation Leo. Distance 2,650 million light-years. Redshift 0.1685. VLT UVE's spectrograph captured the optical afterglow within 24 hours. FOR's instruments followed for a month. The spectrum evolved. Early phases showed blue continuum, power law decay. Then, after days, a supernova spectrum emerged. Broad lines, high velocities, expansion over 30,000 kilometers per second. The connection became irrefutable. Gamma ray burst coincident with hypernova explosion. Timing matched within plus or minus 2 days. Nature published the results in June 2003 from the GRACE collaboration. 27 researchers, 17 institutes. The collapsar model explained it. Stan Woosley's 1993 theory validated. The first hypernova identified was SN 1998, BW, luminosity 100 times a standard type IB. Associated with GRB 980425, spatial and temporal coincidence. The burst occurred on April 25, 1998. The supernova appeared in the same galaxy, ESO 480-G30. Distance 40 megaparsecs. Now the light curve and spectrum matched type ice characteristics. Hydrogen poor, helium poor, oxygen and iron lines prominent, but the kinetic energy was extreme, approximately 2 times 10 to the 52 ergs. Normal type Ike events released 10 to the 51 ergs, 20 times less. The ejecta mass exceeded 10 solar masses moving at relativistic fractions. The radioactive nickel mass reached 0.4 solar masses. High nickel yield powers, extreme luminosity. Not all hypernovae produce detectable gamma ray bursts. Jet orientation matters. The relativistic beam is narrow, opening angle 10 degrees or less. Only observers within the beaming cone see the GRB. Miss the cone, see only the supernova. For every burst detected, hundreds of hypernovae explode unseen in gamma rays. Radio and X-ray follow-up can reveal the hidden jets. Off-axis signatures, delayed brightening, jet deceleration, but many events lack follow-up. They appear as unusually energetic supernovae without the GRB label. Classification based on kinetic energy and spectral evolution. The progenitor pathway involves binary evolution. Mass transfer strips the hydrogen envelope. The companion pulls material, or common envelope evolution. The core, star, and companion orbit inside shared envelope. Friction spirals them inward. The envelope ejects. 2 stars remain. Close orbit. One evolves faster, collapses first, forms a neutron star or black hole. The second star then loses its envelope to the first compact object. Finally, the second star's core collapses. Rapidly rotating, jet launching, hypernova. The binary history imprints rotation. Single stars lose angular momentum through winds. Binary processed stars retain spin. Spin is the key. No rotation, no jets, no hypernova. Just a standard core collapse. Number 4. Electron capture supernova. The middle ground. Stars between 8 and 10 solar masses. Too massive for white dwarf formation. too light for iron core collapse. These develop degenerate cores of oxygen, neon, and magnesium. Core mass, around 1.4 solar masses. Chandrasekhar limit, but the core is not iron. It is Voynog. Density climbs, temperature climbs, electrons pack tighter. Quantum mechanics forces electrons into higher energy states. Degenerate electron pressure supports the core. But at densities above 10 to the 10th grams per cubic centimeter, electron capture begins. Neon-20 and magnesium-24 nuclei absorb electrons. The reaction sequence goes neon-20 plus electron converts to fluorine-20 plus neutrino. Then fluorine-20 plus electron converts to oxygen-20 plus neutrino. Electrons vanish, pressure drops, the core cannot support itself. Collapse. The collapse is rapid, but not as violent as iron core collapse. The neutrino burst is smaller. The explosion energy is lower, approximately 10 to the 50th ergs. 1/10 a standard supernova. Ejecta mass is small, under 2 solar masses. Nickel production is minimal. Light curve fades quickly. Rise time 12 hours to 8 days. Decay time 1 to 50 days. The low energy and fast evolution distinguish electron capture events from more massive core collapses. SN 2018. AZ-D provided the first convincing case. Discovered May 20th, 2018 in galaxy NGC 2546. Distance 31 megaparsecs. Pre-explosion Hubble images showed a faint progenitor candidate. Luminosity and color matched a super asymptotic giant branch star. Mass estimate 8 to 9.5 solar masses. The explosion showed low energy. Kinetic energy around 2 times 10 to the 50 ergs. The spectrum revealed unusual composition. Enhanced calcium, deficient in iron peak elements. The circumstellar material was chemically enriched. Flash spectroscopy in the first days captured narrow emission lines from material previously ejected. The composition matched theoretical predictions for super AGB winds, oxygen, neon, and magnesium burning products. Nature Astronomy published the analysis in June 2021. 6 criteria defined electron capture supernovae. SN 2018, ZD matched all 6. Progenitor mass, circumstellar material, chemical composition, explosion energy, light curve morphology, nucleosynthesis yields. The Crab Nebula supernova of 1054 AD may have been an electron capture event. Chinese and Korean astronomers recorded the guest star, visible for 8 months, daytime visibility. The remnant today shows unusual features. The central pulsar has low velocity, 30 km per second kick. Standard core collapses impart kicks of hundreds to over 1,000 kilometers per second. Electron capture explosions are more symmetric. Fast detonation, weak kick. The nebular composition shows calcium enhancement, low iron. The progenitor mass estimates from stellar evolution models fall into the 8 to 10 solar mass range. The timing matches, the location matches, the physics matches. But definitive proof requires more examples. The sample size is one confirmed case. Statistics need dozens. Electron capture supernovae may explain some fast transients. Faint, rapidly evolving events, rise in days, fade in weeks. Transient. Name server catalogs thousands of unclassified events. Many lack spectroscopy, photometry. Alone cannot confirm mechanism. But the predicted rate is 1 to few percent of core collapse supernovae. In a sample of 10,000 core collapses, expect 100 to 300 electron capture events. Finding them requires fast cadence surveys, early spectra. Detailed progenitor studies, Zwicky Transient Facility, Rubin Observatory Legacy Survey starting 2025. Detection rates will climb. Number 5, Type IX supernova, the failed Type Ia. White dwarf thermonuclear explosions that do not destroy the star. Discovered as a distinct class in the 2010s, 4.5% of all thermonuclear supernovae, fainter than normal Type Ia. Peak absolute magnitude -14 to -19. Normal types Ia hits -19.3 consistently. Type IX shows 7 magnitude spread. Faster evolution. Decline rates steeper. But unlike Type IIS, some IX events leave a bound remnant. The white dwarf partially detonates, then survives. The mechanism involves a white dwarf accreting from a companion. Mass approaches Chandrasekhar limit. Central density climbs. Carbon ignites. But the ignition is off-center. Convection mixes the burning region. The flame front propagates. Deflagration, subsonic burning. The star expands. Density drops. The transition to detonation never happens. Detonation requires high-density sustained compression. Deflagration alone is too weak. The outer layers unbind. Escape velocity exceeded, but the core remains gravitationally bound. a zombie white dwarf, burned, scarred, still intact. SN 2002CX was the prototype. Discovered May 16, 2002 in NGC 5440, distance 8.1 megaparsecs, peak magnitude minus 14.5, 5 magnitudes fainter than standard IAI. Spectrum showed iron lines, intermediate mass elements, low velocities, expansion only 2,000 kilometers per second. Normal IA ejecta moves 10,000. The light curve declined rapidly. Within 30 days, half the peak brightness lost. Hubble follow-up in 2008 showed a faint source at the supernova position. A surviving remnant, luminosity and color consistent with a hybrid white dwarf. Carbon-oxygen core with helium and metal-rich outer layers. Type IAX events occur in young stellar populations. Host galaxies show active star formation, late-type spirals, irregular galaxies, dwarf galaxies. The companion star is likely a helium star or main sequence donor. Mass transfer stable, accretion rate moderate. The white dwarf grows slowly, carbon-oxygen mixture stratified. When ignition occurs, the mixing is incomplete. Nickel production is limited. Lower nickel mass equals fainter peak. The ejecta mass is only 0.3 to 0.9 solar masses. The rest remains bound. The remnant could accrete again, reignite again. Multiple eruptions possible over megayears. SN 2024 BFU and SN 2025 QE are recent examples, discovered by Zwicky Transient Facility, classified by GOTO. Photometry showed early light curves with shallow rises. Nearly linear ascent to maximum. Normal supernovae show power law rise. The shallow profile indicates extensive mixing. Nickel 56 distributed to outer ejecta, early heating, reduced rise time. Monthly notices published light curve analysis in November 2025. The sample of type IAX events now exceeds 50, confirmed. Spectroscopic diversity is significant. Some show helium, some show hydrogen, some neither. The progenitor channels vary, but the common thread is incomplete explosion, failed detonation, bound remnant, survival, number 6, ultra-stripped supernova, the bare minimum, core collapse in a binary system where the progenitor has been stripped almost completely to the metal core, helium envelope removed by mass transfer to a neutron star companion, final envelope mass less than 0.1 solar masses. The exploding core is naked, 1.5 solar masses of oxygen, neon magnesium or iron, barely above Chandrasekhar mass, tiny envelope. When core collapse happens, very little material ejects. Total ejecta mass 0.05 to 0.1 solar masses. The light curve is faint, fast, rise time 12 hours to 8 days, peak luminosity 10 to the 41 to 10 to the 42 ergs per second, decay within 50 days. Expansion velocity 5,000 to 10,000 kilometers per second. SN 2005, EK is a candidate. Discovered January 7th, 2005. Peak magnitude minus 15. Rapid decline. Faint. The spectrum showed calcium and oxygen, minimal iron, low nickel production, ejecta mass estimate 0.3 solar masses, but no direct progenitor imaging existed. The binary companion was not confirmed. Later, surveys found similar events, ZTF discoveries, ATLAS detections, photometric evolution matching ultra-stripped models, but spectroscopic follow-up is challenging. The events are faint. Distant hosts require large telescopes. Fast cadence required to catch the brief peak. The formation channel is specific, a massive binary. Primary star evolves, expands, fills Roche lobe, mass transfers to secondary, primary loses hydrogen envelope, helium star remains, helium star evolves, core collapse, supernova, neutron star forms, system survives. Now neutron star plus helium star evolves, expands, fills Roche lobe, mass transfers to neutron star, helium star loses helium envelope. Naked metal core remains, core evolves, iron core or ONMG core forms, core collapses, ultra-stripped supernova, second explosion, double neutron star system results, tight orbit, orbital period hours to days, gravitational wave emission, and spiral over millions of years. Eventually merger, kilonova. Most double neutron star systems observed likely formed through ultra-stripped supernovae. Low kick velocities preserve the binary. Symmetric explosions, fast detonation, neutrino-driven but weak, kick under 50 kilometers per second. The orbit remains bound. The eccentricity is low. Examples include the Hulse-Taylor binary, PSRB 1913 plus 16. Orbital period 7.75 hours. System losing energy to gravitational waves. Periastron advance measured. Nobel Prize 1993. That system likely went through ultra-stripped phase. No other formation channel produces such tight, compact binaries. LIGO-Virgo gravitational wave detections of double neutron star mergers test these models. GW170817 was the first, August 17, 2017, signal from NGC 4993. Distance 140 million light-years. Component masses 1.46 and 1.27 solar masses, total mass 2.74. Merger produced a kilonova, electromagnetic counterpart detected. Spectroscopy showed our process elements: strontium, tellurium, lanthanides, heavy element nucleosynthesis confirmed. The progenitor binary likely had ultra-stripped supernovae in its history. Both neutron stars formed with minimal kick. Low eccentricity, tight orbit, in spiral to merger over cosmic time. Number 7, kilonova, not technically a supernova, not stellar core collapse, binary compact object merger, 2 neutron stars, or neutron star plus black hole. In spiral, driven by gravitational wave emission, final plunge, collision, merger. The densities exceed nuclear density, neutron degeneracy pressure overwhelmed, temperature spikes to billions of degrees, a hypermassive remnant forms, lasts milliseconds, then collapses to black hole. During those milliseconds, tidal forces shred the neutron stars. Material ejects, neutron rich, free neutrons abundant, rapid neutron capture process begins, our process. Iron nuclei soak up neutrons, build to heavy elements, gold, platinum, uranium, the heaviest natural elements. The ejecta is small, 0.01 to 0.1 solar masses, but the radioactive decay is intense. Half-lives days to weeks. Decay energy heats the expanding cloud, optical emission peaks after days, infrared emission dominates after weeks. The color evolution is diagnostic, early blue, lanthanide poor ejecta, late red, lanthanidae-rich ejecta. The spherical symmetry was unexpected. Previous models predicted flattened disks, accretion disk geometry, polar jets, equatorial torus. But observations of AT 2017 GFO showed spherical expansion. Early epochs, blackbody spectrum, high sphericity. The magnetic field from a hypermassive magnetar may redistribute the ejecta. Magnetic bomb hypothesis. When the remnant collapses, magnetic energy releases, drives spherical outflow. Kailanova luminosity is 1/10 to 1/100th of supernovae. Peak absolute magnitude -15 to -17, but the duration is longer, weeks to months. The R process signature is unique. Spectral features from strontium, yttrium, tellurium, lanthanides, actinides. Elements that supernovae do not produce efficiently. The yields are critical for galactic chemical evolution. All the gold in Earth's crust came from neutron star mergers. All the uranium in nuclear reactors. All the platinum in catalytic converters. The solar system's heavy element budget traces back to ancient kilonova events billions of years before the sun formed. GRB 230307. A on March 7, 2023 was a long duration burst from a kilonova. Duration 200 seconds. Long bursts usually mean supernova, but the afterglow showed red color, kilonova signature. JWST spectroscopy detected tellurium, rare element, R process confirmation. The burst defied classification, long duration, kilonova origin, neutron star merger. The jet geometry may explain it. Off-axis observer, jet viewed from side. Extended gamma ray emission, cocoon breakout, not the collimated beam. Fermi detected it. Swift followed up. Hubble imaged the fading optical transient. Distance 1 billion light years. Host galaxy identified. Low metallicity. Star forming. The heavy elements from this single merger will seed future generations, pollute the interstellar medium, enrich molecular clouds, build into planets. The rate of kilonova is uncertain. LIGO observed 2 neutron star mergers in 3 observing runs. O2 detected GW170817. O3 detected GW190425. No electromagnetic counterpart for the second. Distance too far. Localization poor. O4 started May 2023, runs until June 2025, then 2-year downtime. O5 begins 2027. Detector upgrades, sensitivity improvements, detection range doubles. Rate predictions vary. Conservative estimates suggest 1 to 5 detections per year during O5. Optimistic models predict 10s per year. The uncertainty comes from merger rate density, volume coverage. Electromagnetic follow-up efficiency, survey depth. Rubin Observatory will transform kilonova discovery. LSST starts 2025. Whole southern sky every few nights. magnitude limit 24. Volume reached to redshift 0.5. Forecasts predict several tens of lensed supernovae per year, kilinovae included. Strong lensing magnifies distant events, makes them detectable. SN 2025-WNI showed this works. Lensed superluminous supernova at redshift 2. Without lensing, magnitude 25, too faint for spectroscopy. With lensing, magnitude 20, spectrum obtained, classification confirmed. Kilinovae at high redshift can probe early universe merger rates. Metal-poor environments, first-generation neutron stars, cosmic evolution of heavy elements, so 7 types, 7 mechanisms, 7 extremes. Pair instability obliterates the most massive stars, leaving no remnant but seeding the cosmos with heavy elements. Superluminous events outshine entire galaxies powered by magnetars or circumstellar shocks or radioactive decay at unprecedented scales. Hypernovae launch relativistic jets drilling through stellar envelopes, creating gamma-ray bursts and black holes. Electron capture supernovae detonate the cores of intermediate mass stars through quantum pressure collapse. Type IX events are failed thermonuclear explosions, leaving zombie white dwarfs that survive to accrete again. Ultra-stripped supernovae are the faintest core collapses from stars stripped bare by binary mass transfer, forming tight double-neutron star systems destined to merge. And kilinovaes are the collisions of neutron stars themselves, forging gold and platinum in neutron-rich ejecta that colors the universe. Each type obeys different physics, each leaves different remnants, each enriches the interstellar medium with different elements. Together, they span 7 orders of magnitude in energy, from 10 to the 48th to 10 to the 53 ergs, from hours to years in duration, from single stars to mergers, from pure thermonuclear to pure gravitational. The taxonomy is not complete. Discovery continues. In 2024 alone, over 23,000 supernova candidates were reported to Transient Name Server. 2,177 were classified, 1,533 type IA, 70 type IKE, 52 type Detune, 30 type SLSN-I. The diversity grows. New subclasses emerge, transitional objects, hybrids, events that defy clean categories. The universe is running an experiment. Billions of stars, billions of deaths. Each one tests stellar physics at extremes. We catch a few thousand per year, observe a few hundred in detail, model a few dozen comprehensively. From those we build theory. We predict what happens at temperatures of billions of degrees, densities exceeding atomic nuclei, magnetic fields 10 trillion times Earth's, gravitational fields warping space-time, velocities approaching light speed. We cannot reproduce these conditions in labs. We can only observe and deduce. In 2040, the gravitational wave observatories reach next-generation sensitivity. Laser arms 10 times longer, strain sensitivity 10 times better, volume coverage 1,000 times larger, detection rates climb to thousands per year. Every merger will have electromagnetic follow-up, every kilonova will be studied, every jet will be mapped, the population statistics will be complete. We will know which progenitors produce which explosions. We will trace the cosmic evolution of each supernova type from high redshift to today. We will measure the heavy element contribution from each channel. We will close the loop on stellar evolution, from birth to death for every mass, every metallicity, every binary configuration. But today we work with fragments, incomplete samples, biased surveys, distant galaxies where only the brightest events are visible, nearby galaxies where faint transients hide. Selection effects everywhere. We correct for them, we model them, we propagate uncertainties, we compare theory to observation, iterate, refine. The process is slow. It takes decades. It takes thousands of researchers. It takes global telescope networks and space missions and detector arrays spanning continents. It takes careful data reduction and statistical analysis and cross-validation against independent observations. Hypernova GRB 030329 was studied by the VLT in Chile with UV-EAS and 4S spectrographs, tracking the optical afterglow for 1 month. 27 authors from 17 institutes analyzed the data. Nature published in June 2003. That collaboration included European Southern Observatory, University of Copenhagen, Stockholm Observatory, and institutes across Germany, Italy, Netherlands, United Kingdom. The result was ironclad. Gamma-ray burst, linked to supernova. Expansion velocity, 30,000 kilometers per second. Kinetic energy exceeding 10 to the 52 ergs. Progenitor mass over 25 solar masses. The paper cited Woosley's collapsar model from 1993 and validated it with observations. Electron capture supernova 2018, ZD, was analyzed by University of California, Santa Barbara, Las Cumbres Observatory from multiple international partners. 6 criteria checked. Progenitor identified in pre-explosion Hubble images, super AGB star. Mass 8 to 9.5 solar masses. Explosion energy 2 times 10 to the 50 ergs. Chemical composition enhanced calcium deficient iron. Flash spectroscopy showed circumstellar material with oxygen, neon magnesium burning products. Light curve rise and decay timescales matched theoretical predictions. Nucleosynthesis yields consistent with electron capture on neon and magnesium. Nature Astronomy, June 2021. The paper concluded this was the first robust identification of the third core collapse supernova mechanism after iron core collapse and pair instability. Type I superluminous supernova catalog reached 262 events by December 2022. Finding luminous and exotic extragalactic transients program, FLEET, led by researchers at University of California, Berkeley, Harvard-Smithsonian Center for Astrophysics, Las Cumbres Observatory. Over 30,000 photometric detections compiled, UV optical IR bands, light curve modeling applied to every event, magnetar plus radioactive decay hybrid model, physical parameters derived, ejecta mass, magnetar spin period, magnetic field strength, nickel mass, results published, monthly notices. November 2024, data released on GitHub and Zenodo as open source resource. The catalog enables population studies, correlations between parameters, redshift evolution, host galaxy properties, progenitor mass distribution peaks at 6.5 solar masses, no significant subclasses identified, continuum of properties, the tools exist, the data accumulate, the understanding deepens, every detection refines models, every spectrum tests theory, every light curve constrains parameters. The 7 types are not static categories. They are frameworks, useful for organizing observations, for communicating results, for building intuition, but nature does not care about our labels. Stars explode according to physics. We measure, we classify, we interpret. And slowly the picture sharpens. A final fact from a recent discovery. In October 2024, researchers analyzing LIGO Virgo O3 data found anomalies in neutron star merger models. The heavy element abundance in the universe exceeds predictions from observed kilonova rates. Gold, platinum, uranium. Too much. Either the merger rate was higher in the past, or other mechanisms contribute. Long-duration gamma-ray bursts from collapsars might produce our process elements, the jet-driven winds, the accretion disk outflows, or evolved stars in their giant phase could undergo slow neutron capture, building heavy elements over time. Each scenario has problems. The merger rate evolution requires specific assumptions. The supernova R process yields conflict with nucleosynthesis models. The stellar evolution channel lacks observational evidence. The discrepancy remains unsolved. Published May 20 to 24. Big Think article covering research from multiple institutions. The origin of gold does not add up. 7 years after the first kilonova detection, the question reopens. That is the nature of astrophysics. One discovery answers old questions, opens new ones. The 7 types of extreme supernovae are known, observed, catalogued, but the details are incomplete. The progenitors are uncertain. The mechanisms are debated. The contributions to cosmic chemical evolution are unresolved. We know enough to classify, not enough to predict. The next decade will change that. New surveys, new detectors, new missions. JWST probing high redshift. Rubin surveying deep and fast. Next generation gravitational wave observatories, hearing more mergers. The data will flood in. The theories will be tested. And the 7 types will become 7 understood mechanisms with quantified rates and confirmed progenitors and measured yields. Until then, we observe. We analyze, we publish, we refine, piece by piece, event by event. The picture of how stars die becomes clear.